The following program is video supplemental instruction. VSI is brought to you by the Teaching Center, UF's Learning Support Center, www.teachingcenter.ufl.edu.
Okay, so I'm going to work through problem number 3 for Physics 2020 Midterm Exam 2, year 2006. And this problem says, a wheel of radius 10 centimeters and moment of inertia of 30 kilograms meters squared experiences a constant force of 50 newtons as shown in figure quote-unquote wheel. What is the angular acceleration? Okay, and so you've been giving as part of the exam, you were given the supplemental sheet that has figures on it, and if you look at the figure for wheel, I've basically reproduced it here, where we have the wheel, and the radius of the wheel is 10 centimeters or 0.1 meters, and we have a force that's acting on the wheel that's acting up. That's causing the wheel to rotate. Alright? And so it's asking us, what is the angular acceleration? So basically, what is the acceleration of the wheel when we apply that force? What's the rotational acceleration of the wheel as we apply that force? So I want to give you just a quick background. In order for you to understand this problem and work through it, you have to understand that there are two different types of, we have translational motion and rotational motion. And basically they're analogous to each other. And so basically translational motion is basically linear motion in a straight line. And so when we're talking about translational motion, we talk about mass. And if we're talking about rotational motion, we're not talking about mass, we're talking about moment of inertia, which is normally denoted by the capital I. Translational motion, we'll be talking about velocity, usually v. And for rotational motion, we talk about angular velocity. Translational motion, we'll talk about acceleration, and for rotational motion, we'll talk about angular acceleration. Newton's second law says for translational motion that the sum of the forces is equal to mass times the acceleration. If we're talking about rotational motion, we're talking about torque, which basically is the rotational force that's needed to cause something to rotate, and that's defined as the radius or the distance between the pivot point, that vector, cross the force vector that's applied to that particular point. Alright? And so in this problem we're going to be dealing with rotational motion because we're talking about a wheel and we're applying a force that's going to cause that wheel to rotate. And so one thing that you need to know is that torque is equal to R cross F, which is what we have here. So basically that's the cross product of the distance vector times the force, which is equal to basically R times, we usually call it the perpendicular force. Alright? And the reason why we call it the perpendicular force is because it's always the force that's acting in the y direction. For example, let's see, if we had, let's say, another wheel, okay, or let's just say we had a pivot point here, and this is distance r, and let's say that we had some force acting at this point that's going to cause basically this object to rotate, so it'll cause it to rotate. Then we could actually resolve this, we can resolve this force vector into two components, the x component and the y component. all right? And basically, the force that we're always going to use, if you talk about this force here, this force is not going to cause this particular object to rotate because you're just pulling it straight out. But the only force that's actually that causes this object to rotate is the y force, okay? And the y force just happens to be perpendicular to the object that we're trying to rotate. And so that's the reason why we call it the perpendicular force. And whenever you're working with problems like this, you always want to set up your x and y axis so that this angle, theta, will always equal to pi over 2, okay? So that, you know, it makes it easier to work with. But if you want to see a more detailed explanation and derivation of how we get to this, so basically we just said that the torque is equal to R times the perpendicular force, but the perpendicular force is equal to the force is equal to the force times the sine theta. All right, we already said that is equal to R F times the sine theta, okay? Because we said that Fy is going to equal to your R times your F times the sine of theta, okay? So if this is theta here, it'll be theta there. If you want to see a more detailed explanation of how we get this, please go to the additional supplemental video where I talk about how to derive the expression for torque. Okay, but for now, just take it for granted that these expressions are true. All right. So since we know that this is true, then we said earlier that the torque is analogous to the Newton's second law for translational motion, which is the sum of the forces equal to mass times acceleration. And, okay, so torque, which is tau, is equal to, in rotational motion, mass is the moment of inertia. Okay, so that's basically I. And acceleration is angular acceleration, so that is alpha. All right, and so we know that the torque is also equal to R times F times the sine of theta. Okay, but we know that sine of theta is just equal to 1. Because theta is equal to pi over 2. Alright, so this really is just equal to R times F. Okay, so it's just equal to the distance from the pivot point times the force that's applied. Alright? That's good to know, because then that allows us to solve, this expression allows us to solve for angular acceleration, because we've been given all the other information in this problem. Okay, we know the moment of inertia, and we know the distance, and we know the force that's applied. So we have moment of inertia times alpha is equal to R times F. We want to solve this equation for alpha, so that's going to be R times F divided by the moment of inertia. So the angular acceleration is going to be the distance, which is 0.1 meters, multiplied by the force that was applied, which is 50 newtons, but newtons is kilograms, meters per second squared, divided by moment of inertia, Now, let's see, over here, moment of inertia is basically defined as m times L squared, but this was actually given in the problem as 30 kilograms times meter squared. And so, but in a general case, the moment of inertia is basically your mass. So this is a mass multiplied by a length squared. Okay, and as you can see, the moment of inertia given in this problem is a mass times a length squared. And so that's given, so we can use that. And when you solve for this problem, you should get, you have a meters and a meters, that'll cancel out with this meters squared, kilograms and the kilograms, okay? So all we're left with is a per second squared, but since we're talking about rotational or angular acceleration, instead of a distance, we're talking about radians or an angle. So the actual units are going to be, when you work this out, it's going to be 0.17 radians per second squared. Okay, and this is the actual answer, and it's actual radians because really it comes from when we substitute in pi over 2 radians into this equation. That's where the radians come in. That's how we get radians per second squared. Okay, so indeed that is the answer.
The Teaching Center, UF's Learning Support Center, www.teachingcenter.ufl.edu.